Hi, I'm Todd Austin. I'm a professor at University of Michigan and also one of the founders of the data privacy startup, Agita Labs. This presentation is about Mojo-V. Mojo-V is an instruction set extension for the RISC-V open source instruction set that enhances a RISC-V processor to be a privacy-enhanced technology, allowing it to compute on data that the software or programmers cannot see, making it a true privacy technology. Mojo-V is designed to be very simple and easy to add to an existing design. With this short presentation, I'm going to introduce you to the technology and then tell you more about the Mojo-V project. But first, I want to talk about why security isn't very secure in today's world and how Mojo-V then goes on to address these critical issues. There's really only two things you need to solve to make your system highly secure. First, you got to solve the trust problem with software and the people that deal with software, developers, IT staff, etc. The problem with software is it's full of bugs, and many of those bugs can be turned into security exploits. And the infrastructure we have for finding and fixing those exploits isn't very effective. So pretty much all software contains bugs that attackers can potentially turn into security exploits. Even if you could find and fix all those security vulnerabilities, you still have to trust that the programmers are not going to siphon off your data and use it in ways that you don't intend them to do. And often developers prioritize their corporate interests over the interests of the users of their software. So establishing that human trust with developers can be very difficult. Let's say you were able to establish that trust, and to write a perfect program, you'd still have to deal with the other side of the security coin, which is side channels. Side channels are when publicly observable properties of the system leak information about the secrets inside of it. And in modern computing systems, this can come from how the system accesses memory, how the timing of the operations or the API calls occur, how it's interacting with its cache, how it's speculating or misspeculating as a microprocessor. All these things can leak information and have been demonstrated to do so. Security is not very good in today's world. So really the goal of Mojo-V is to deploy a highly secure, very efficient, and simple privacy mechanism for RISC-V. As a secondary goal, we want to make a consumer-grade alternative to nascent fully homomorphic encryption. The usage model of Mojo-V is pretty much the same as fully homomorphic encryption, although Mojo-V is a bit easier to program. I'll talk more about the security differences and the performance differences, which are quite vast, later in this short presentation. Mojo-V is a zero trust technology for RISC-V. Let's talk about what zero trust is. It's a big trend in computer security today. It's a bit misnamed because there really is no such thing as zero trust. It would be better named less trust, but I have to admit less trust is not a very good name. So what zero trust does is it removes trust in part of the system to concentrate the trust that is left onto a smaller part of the system. And then we try to make that smaller part of the system harder to hack. And that is really an effective approach at making systems difficult to hack. Just to give you a real life example. Have you ever walked into a hotel and when you're checking into the hotel, they have a plate of cookies on the table and there's a little sign that says, please take one cookie. That's a full trust system because every person that walks past that plate of cookies, you have to decide whether or not you have to trust that person to only take one cookie. If one of my kids, for example, walks by that plate, they're probably going to take a bunch of cookies. So the system breaks down pretty fast. A zero trust system would be to minimize the amount of trust. So we're going to put the trust in this case into the person behind the check-in desk, and they're going to lock the cookies with a key and a lock. And so we're not going to lose cookies, and we only have to trust that person behind the desk to not lose the key and not to give away more than one cookie to each customer. The functional definition for a computer is such that with a zero trust system, we're redirecting trust away from non-durable technologies to more durable security technologies. So as we saw before, we want to move trust away from software, compilers, runtime, operating systems, and the people who deal with those things, developers and IT staff. So we want to move trust away from them. Where we want to concentrate our trust is into more secure technologies, such as strong cryptography and verified secure hardware. That's what Mojo-V does. And it very effectively eliminates trust with software and developers. So now let's take a look at how you can implement zero trust technology for an instruction set like RISC-V. And the goal here is to take security of a RISC-V system from good, where it is today, to great. Not perfect. There is no perfect security, but great, such that it is so difficult to attack and penetrate that Mojo-V enhanced system that the attacker will likely go on to some other system to do that. The first thing is we don't want to have to find and fix the vulnerabilities in the software or the hardware. We want our security to be strong despite all of those vulnerabilities in software and hardware. So we're going to use a technology that I've been developing for the last 10 years called sequestration. With sequestration, we take our sensitive data and we lock it into a place in the hardware where we know it can't be seen or lost. In Mojo-V, sequestration happens in the secret registers, which is a band of the bottom 4 registers in the integer and the floating point register files. When you turn on Mojo-V, those bottom registers are sequestering sensitive data. We'll see what that means. And the only place you can go from those secret registers is to third-party encrypted memory. That's with a special instruction that stores the value to memory, and when it arrives, it's encrypted under some other person's key, a third party, presumably the person who cares about that data the most. When you're living in those registers, those secret registers, we have to prevent software and the people associated with software from seeing the data in those registers. So Mojo-V, when you turn on Mojo-V, the secret registers have a special register calculus that prohibits disclosure. It's not possible to take a value in a secret register and put it somewhere where a programmer can inspect that value. Moreover, when you turn on secret registers and Mojo-V, the system eliminates the possibility that the programmer who is computing with normal RISC-V instructions out of the secret registers could create a behavior in the software that would leak sensitive information, essentially eliminating side channels. This is done by enforcing in Mojo-V only the instructions executing out of the secret registers, enforcing what's called data-oblivious execution. That's where the instructions that are executing on that sensitive data are guaranteed by the underlying hardware not to reveal by their timing, their conflicts in the cache, their microarchitecture usage, what the information they are computing upon. And that's a very simple change in the microarchitecture to do that. Mojo-V is called Mojo-V because it's a 5th generation framework for secret computation. Starting in 2017 with my work that I co-built called Morpheus, which was a system that had encrypted pointers and code. That later led to a DARPA project where we developed Morpheus 2 that encrypted data all the way up into the pipeline. That was built and put into a DARPA competition. That machine was red teamed for 3 months. It was never penetrated. That then led to the work of my former PhD student, Lauren Biernacki, who developed basically a technique to take that encryption out of the pointers and code and move it directly to the data you care about. I want to encrypt this social security number. And she created this structure called the SE, sequestering encryption functional unit. And then that technology led to G Labs, which commercialized that technology in the AWS and Azure clouds. And then that technology was both red teamed as well as formally verified. So in Mojo-V, we really have the end result of all of those previous efforts to generate a very minimalistic and highly secure secret computation capability for RISC-V. So let's take a look at what secret computation looks like to a programmer. First of all, secret computation is blind and silent. Blind means no disclosures. You cannot move data out of the secret registers into non-secret space. The only place you can move it is to another secret register or to third-party encrypted memory. It's also silent, which means that when you're executing on secret values out of secret registers, you're forced to do that in a data-oblivious manner. Let's take a privacy-enhanced application example and see how it would work with Mojo-V. In my home, I have a camera in my backyard that takes a continuous video stream and sends it up to the cloud. Now, it's encrypted on the way up to the cloud, but it's not encrypted in the cloud when it's analyzed by typically a machine learning framework to determine what's happening in my backyard. So I have to trust that service provider that they're not going to watch and see what's happening in my backyard. And if a judge comes by, the service provider say, give me that information. I mean, they have to reveal that information. And they have that information because it's all done in the clear. They hold the keys to decrypt that data. They can see what's happening in my backyard at any time. With Mojo-V, my camera, which is the data owner, we call that the data owner, has a key. It will encrypt that data, and it will share that encrypted data and an encrypted version of the key with the service provider. That key is encrypted using what's called public key infrastructure. We take the public key of that little RISC-V processor with Mojo, and we encrypt the key under that. Embedded within that hardware is the secret key. This is a standard technology used for web certification. It was invented in the 70s, and it's really the backbone of how we create trust in the internet today. We're just adapting that to this microprocessor computation capability. It's possible for that RISC-V processor with Mojo-V to essentially unencrypt that key in hardware in a way that none of the software or operators in that service provider's installation can see that key. Only the hardware can see it. And now the hardware can direct secret computation on the encrypted data coming from the camera in my backyard. Can perform machine learning computation on it, whatever. And when those classifications are produced, they have to be stored to memory, encrypted under the data owner's key. There's no place in the computation where the service provider can see what is happening in my backyard or what the image looks like. It comes back to me, and I can decrypt it and see it on my timeline. So now the service provider is providing a capability for me, but they don't have the ability to see the data that they're computing upon. And that is the essence of a privacy technology. Well, the approach we're going to use to implement this is we're going to introduce these secret registers into RISC-V, basically take over a few of the registers on the bottom of the register file, 4 on the integer and 4 on the floating point register file, and we'll introduce those semantics into the Mojo-V enhanced RISC-V core, and then we're also going to implement third-party memory encryption through 2 instructions, an encrypted load and encrypted store, where a third party can inject a key into the system, and then the programmer can then encrypt, load data under that encryption key and store data under that encryption key, only to secret registers. Mojo-V is designed to be deployed and used and efficient and easy to program. Okay, so it has a very small footprint on the underlying RISC-V hardware. It works completely with the existing instruction set. Once you turn on the secret registers, the way you compute out of secret registers is just using the RISC-V instruction set. It adds a mode bit to turn this capability on and off, and a program can turn it on, use it for a while, and turn it off. When it turns it on, all the computation out of those bottom 4 register file, the secret registers, is under secret register semantics and can only go to and from encrypted third-party memory. All the rest of the registers are just like normal RISC-V. So there's no change to the rest of the machine, and you can easily intermix secret and non-secret computation as you would likely do for any type of large application. We designed this to be enforced 100% in the decode stage of the pipeline, so that you don't have to worry about all the details of secret computation and the register renaming and the out of order issue execution, et cetera, et cetera. there's really minimal impact to the rest of the microarchitecture. All this enforcement occurs in the decode stage. And then unlike other security technologies that we've seen in the past, there's no storage tags here. There's no need to know what's a secret value and what's not a secret value. The secret values are in those bottom 4 registers. So there's no tagging of memory, there's no tagging of registers, etc. And then unlike fully homomorphic encryption and other privacy technologies, there's no advanced cryptography involved. This is all just standard cryptography. Let's take a look at those secret register semantics in the context of an actual system. So again, we have our data owner. She has a key here. She produces some information that she encrypts under that key, and then encrypts that key under the public key of the RISC-V core enhanced with Mojo-V. That allows that piece of hardware to expose that key, and now we can do an decrypted load into the secret registers. Okay, but only into the secret registers. And in the secret registers, we get this sequestration capability where we're computing on the data. The data is not encrypted. We're computing on it, but the program cannot know what the values are in those registers. At some point later, you may want to spill a register, or you may want to send that information back to her, and you're going to do an encrypted store, and then that ciphertext can be sent back to her, which she can use her key, and she's the only one that can do this. She can use her key to decrypt that, the result of that computation. And then over here, again, we got the service provider. But you see on this slide, I've kind of expanded what it means to be a service provider. Either it's, it's the web service provider I'm interacting with, or it's an attacker that's hacked into a system that I'm interacting with, or it's a developer, honest or malicious, who's dealing with my data, or it's a piece of malware or an IT staff member, honest or malicious. So none of these entities can see the data that is being computed on by the Mojo-V secret registers. Now, why is that? That's because to see that data, right? To see that data, one of the following things has to happen. This person needs to be able to move a secret register to a non-secret register so you can just move it to wherever you want and inspect it. That's disallowed in decode. Alternatively, this person needs to take a secret register value and create a behavior in the program running that he can recognize and know what that value is. And I'll show you on the next slide that the secret register computation is forced to be data oblivious. There are no behaviors that can be seen by him. So he has no idea, no matter what program he writes, what that value is. And then next, he needs to store a secret register decrypted to memory. That's disallowed. If you use a normal load or store in a secret register, you get an exception. You have to send those values to memory with an encrypted third-party encrypted load or store. So that's disallowed. And then finally, when the encrypted value is in memory, he would have to be able to decrypt that value. We use best-in-class strong cryptography, authenticated, semantically secure cryptography. There is no information in the ciphertext that is stored in that memory. So unless he can guess the large key, he's not going to get that information. So he has no idea what the information is, what her information is that he's computing. He's just providing a computational service and then sending back ciphertext to her. Let's take a look at those secret register semantics. There's a CSR register that materializes when you have Mojo-V enabled hardware. And it has this secret register bit. And when you turn on that secret register bit, you all of a sudden get secret register semantics out of the lower 4 registers of both the integer and the floating point register files. The computation is blind. Now, what that means is that if an instruction has an input, so the secret registers are P0 through P3, they overtake temporary register 3 through temporary register 6. So we repurpose 4 registers to become secret registers. Now, if any input to an instruction is secret, the output has to be secret. That's the sequestration calculus rule. You've trapped information into those registers. That's easy to detect at decode, And if decode sees someone try to write a secret input computation to a non-secret register, you just get a security exception at decode. Second, secret registers can only transfer to and from memory with encrypted loads and stores. You can't take a non-encrypted load or a non-encrypted store and send that memory to, then send it to memory. So it's stored under a third-party key once it goes to memory. The computation is also silent. That means that the decode stage for computation that is using as an input a secret register, that computation is forced to be data oblivious. And that means there's 3 things you cannot do with a secret register. You cannot use it as a branch predicate, right? So if you're comparing a secret register to a known value or another secret register or a non-secret register, that is illegal, okay? If you were able to do that, you could create control flow in your program based on secret registers. The second thing you can't do is you can't use a secret register as a code pointer. You can't jump to a secret register address. So you can't JALR, you can't return. So you can't use a secret register. So you just use a non-secret register for that. That's fine. And then third, you cannot use a secret register as a base register for a load or a store, even an encrypted load or store. That's because if you could do that, then you could look at how data memory was being accessed, and that would reveal information about those secrets. Now, in the program, branching on a secret as a predicate is using an if statement on a secret. You're not allowed to do that. That's not permitted. Well, the compiler will let you do it, but what the compiler does is internally, it's going to implement it as predicated execution. It's going to use conditional moves to produce that result. Not allowing a secret register as a base register means that you're not permitted to index into an array structure with a secret. And so the way you get around that is you have to use what's called an oblivious RAM, where you scan the entire array and then you modify one value. So the behavior is never changed based on the index. But I always like to tell people that if you're using an ORAM, an oblivious RAM, that's like drinking in the morning. It's a warning sign that you need to address. And the warning sign here is that your program is designed in an inefficient manner for secret computation. So I have many papers that have shown that if you need ORAMs, you can usually, in fact, in every case we found, you redesign the algorithm to not need an ORAM and be efficient as well. And then I'll just quickly show you this Mojo-V code. So here I've got, I'm loading 2 secret registers. This code it's computing, it's basically got a secret value X and a secret value max. So these particular values, when they're in memory, are encrypted, and they can only be loaded into secret registers. And what I want to do is I want to see is X greater than max, and if X is greater than max, I want to update max because I now have a new max. So I load X, and it's encrypted load. I load max, it's an encrypted load. Now I've got X in P0 and max in P1. And then I just compare. I say, is max less than X? Okay, so this is max, that's X. Is it less than? And then the predicate 0 or 1 is put into this register P2. And then I use this P2 to do a conditional move. In RISC-V, conditional moves are implemented with what's called a C0 instruction. So if this predicate is 0, then this value gets 0. Otherwise, I copy this register into this value. So based on this predicate, if this is true, I get this value. And if it's false, I get this value. And so because I have the same predicate here, and then the sense of these is opposite, one of these will be 0 and one of these will not be 0. So I just OR them together at the end and I get this conditional move. So the updated max values here, I just unconditionally store the max value, either be the same value as before, or it'll be the updated value of X if X is larger. And there are no behaviors in this code to reveal whether or not X or max was updated. You cannot look at the ciphertext to see if X or max has been updated because the ciphertext is semantically secure. So every time I store a value, even if it's the same value, I get different ciphertext. So we are building Mojo-V, and I want to show you the roadmap. One of the things we're building is a specification for this instruction set. We have a draft that we'll be releasing soon for external feedback. And the draft includes, basically what are the secret register semantics, what are the load store semantics, what's the key management infrastructure of the design, and what are the microarchitectural considerations of this design. And then we're enhancing the RISC-V spike simulator to support Mojo-V semantics. We've already done this. It's working very well. In fact, it's only 300 lines of code to enhance it to support these secret register semantics. And then we are enhancing LLVM, the RISC-V LLVM, to support secret variables in C and C++ that you can then use to do secret computation and operate on third-party data. That work is underway right now. Initially, we're going to add this in terms of performance and security analysis. We're going to add this to a Gem 5 RISC-V simulator model so we can look at the performance implications of this technology. And then after that, we're going to enhance the pulp processor from ETH, the Ariane CVA6, to support Mojo-V on an FPGA, which we'll then deploy into the cloud. And then that will be a platform for a red teaming exercise where we'll hire a team to try to penetrate that target. But that also having that RTL level implementation will allow us to proceed with formal verification on that design as well. So we go from spec to working system, and all of this will be open. We will make this available to everyone that wants to track us as we're working on this, and anyone is certainly welcome to grab our repos. Everything will be up on GitHub. This is roughly where we are today. We're just getting started on getting into LLVM. Spike's working pretty well at this point, and we're starting on our Gem 5 model. Looking ahead, some things we want to do is we want to do a good comparison of this technology with fully homomorphic encryption. If you're familiar with fully homomorphic encryption, it's basically a way to manipulate ciphertext so that you can compute directly on encrypted data. The trade-off is as follows. Fully homomorphic encryption is a math-based privacy technology, and Mojo-V is a microarchitectural-based privacy technology. So from a security standpoint, FHE is better than Mojo-V because hardware Trojans and analog direct measurement attacks. So if somebody tries to direct measure your silicon, those attacks will penetrate these initial Mojo-V implementations. On the other hand, FHE has very limited operational capability, only supports adds and multiplies, whereas Mojo-V supports the full RISC-V instruction set minus the operations that would create side channel behaviors. So, it's much easier to program Mojo-V than FHE. And then Mojo-V, we expect, based on our experiences with TrustForce, it'll run about probably 90% of native computation speed. And that's going to be about 10 million times faster than a typical FHE implementation. So the security differences are vast. And I'm not comparing to integer FHE. I'm comparing to like hybrid integer Boolean FHE. So a very capable Turing complete FHE platform. So big difference. And there's no reason why these two technologies can't live together, where Mojo-V can really be this consumer grade privacy technology, easy to program, super fast, super low cost. And then when you need military grade capabilities, you can break out your fully homomorphic encryption and your super expensive large accelerators, et cetera, et cetera. So the world can have both these technologies. And we're not going to rest at 0.9 performance. I want to get this to, I personally believe I can get Mojo-V computation to run faster than native. And I'll tell you why in a second. But some of the things we're going to look at to optimize it, we're going to look at just tagging the L1 and L2 caches so that when we store information in the cache, we mark it as secret information, but we don't encrypt it until it leaves the cache. That's a pretty safe optimization to do because the architect owns the caches, right? We don't have to deal with the memory system and the buses and all that stuff. So I can, as it leaves the cache hierarchy, I can encrypt it. And I can put tag information in my caches. I mean, we already do that in x86 for decoding and stuff like that. So it's not that big a deal to put more tags in the cache. And then if a non-secret operation tries to touch that data, they get an exception. They can't, they just get random information because it should be ciphertext. If you do that optimization, you're going to run pretty much at native speed. We're also going to look at ciphertext caching, where, when you have spills and refills out of those registers, you can cache them, indexing with the ciphertext. Won't create any side channels. It'll just be a place to have a little bit more register space in the microarchitecture. And then also want to look at aggressive prefetch. Data-oblivious programs reveal their addresses very, very quickly. And so I think that because we're forcing data-oblivious execution in the secret computation, the branch prediction accuracy, the prefetch accuracy is going to be so much higher for that particular code. And I think, long term, you'll see it actually runs a little bit faster than just data heuristic native computation. Also very interested, and if people want to reach out about this, I would be delighted to explore this. I'm very interested in how do we integrate these technologies into GPUs, into TPUs, and into NPUs. I think it's pretty straightforward to enhance just about any computational capability with this technology. There's nothing CPU specific about it. You just need to put this encryption capability at your memory interface. You need to define what it means to be secret computation in the microarchitecture, in the architecture, And I think that's certainly possible in these more, AI-oriented architectures. And I think privacy in our AI computation is vitally important. And, we're probably not going to achieve that with, many, many, many times slowdown that you get with FHE. We need something that's a little more consumer friendly if we want to really deploy wide privacy enhanced AI. And then finally, one of my PhD students, Marone Demisier, she's been working on integrity checking and safe disclosures, which is basically a technology that allows you to not only know that your information was not disclosed by a service provider, but the service provider can prove to you how they computed a value. So as I want you to analyze my genome. When the value of my analysis comes back, there's what's called a concise proof that gets attached to it that proves to me whether or not you executed that particular piece of code as we agreed. This is essentially a microarchitecture version of zero knowledge proofs. It's very flexible. And I can use that same mechanism to selectively release information from Mojo-V secret registers to non-secret registers. So for example, you may be doing machine learning training on my sensitive data, but I will allow you to see the last epoch's accuracy when you're done computing a full epoch of computation. You don't get to see the data. I just let you see the error rate from the last test inference. So that's a really flexible thing. So we'll be exploring that as well. This is our team. We've been working on these technologies for a long time. At University of Michigan, also some of us at Addis Ababa University and Princeton University and Ajita Labs, and lots of students and lots of work. This is our main repo, and you can follow our work there. There's not much there right now. We'll soon be releasing the spec, and then we'll shortly after that release the initial spike implementation, reference implementation of Mojo-V. I'd love to hear your feedback. If you have interest, feel free to reach out. We're really interested in working with both academic and industrial partners to help make the world a more safe and private place. Thank you so much. Appreciate your time.